Good evening, all. Welcome to the live session number week 11. Good evening, all. Welcome to live session week 11. We'll wait for a couple of minutes and then get started. Just share my screen. As a quick recap, you can check the formulas over here. In the last week, we discussed on how to calculate entropy for different processes. So basically, change in entropy is defined as integral del Q by T, where the heat transfer is again depends on the process that is the system is undergoing. So it needs to be in a reversible process. But even though del Q reversible is a process dependent, but then when you perform the integral, the delta S that you would be getting only depends on the limits of integration. That it only depends on the initial and the final point, and doesn't depend on the path it follows. So this we have discussed in the last week. And then we also derived some formulas for different processes. For a constant volume process, we have mCv ln T2 by T1. And for a constant pressure process, instead of Cv, we'll have Cp. And for a polytropic process, we have derived this relation in the last week. So you can, if you want to refer, you can go back to the last week's video and then see how these formulas were derived. Similarly, for an isothermal process, we have delta S in terms of mR ln P1 by P2, or you can write it in terms of V1 and V2. Essentially, P1 V1 equals to P2 V2. So this term becomes ln V2 by V1. Now, keeping these equations in mind, we will solve a few more problems this week. So you can go through the first problem. 5-meter cube of air at 2 bar pressure and 27 Celsius is compressed up to 6 bar pressure. So it is undergoing a polytropic process, PV to the power 1.3 equal to constant. It is subsequently expanded adiabatically to 2 bar. So basically there are two processes. Initially it follows a compression process which is polytropic, and then subsequently it undergoes adiabatic expansion. Considering two processes to be reversible, determine the net work done, change in entropy for the compression process, and change in entropy for the expansion process. So how do we proceed further? So how do we calculate the net work done? This we have done from week 1. How to calculate work done in week 2 and week 3 as well. So first we'll write down information that is given to us. So we have been given V1 as the 5-meter cube. P1 is given as 2 bar, and T1 is always convert the temperature to Kelvin. Similarly, we also have been given P2, that is after the compression process, is 6 bar. So do I know anything else there? Do I know volume or temperature? Is not given directly. And then there is a third process after which the final pressure is given to be again 2 bar. So this is the information that is given. So there are two processes, and to calculate the net work done is say 1 to 2, and just write 1 2 and 2 to 3. So there are these two works that we have to calculate. 1 to 2 is a polytropic compression process, and 2 to 3 is an adiabatic expansion process. So what is the work done in expression for work done in a polytropic process? We have derived this previously. So it is mr t1 minus t2 by, in terms of your polytropic index, n minus 1. So, but in order to do this, I need to to use above relation, I need to know T2. T2 is unknown here. So how do I calculate T2? We use again use the polytropic relation over here, PV to the power 1.3 equal to constant. So from there you can get the relation between P and P. So which goes as T power 1 minus n, P power n equal to constant. So from this relation you can get T2. T2 is T1 times P1 by P2 whole power n minus 1 by n. So is this relation correct? Like we have PV to the power n equal to constant. So we replace B in terms of T and P. So we will be T by P, T to the power n by P to the power n minus 1, 1 minus n. So I think there is a mistake here. Basically we have PV to the n equal to constant. And from there we write V in terms of T and P, that is T by P to the power n, which will give us, hi, good evening. Are you connected to two devices or something? There is some echo, so if you can turn off one device. Yeah. So once we have, so from P and B, we can write the equation in terms of T1 and T2. So you have P1 and P2 is already given, 2 bar and 6 bar. So from there you can calculate T2. Once the second temperature is known, you can substitute in this equation to get the work done for the process 1 to 2. So this is for a polytropic process. Similarly, if I want to calculate for an adiabatic process, I would use the same relation again, but then instead of N, it would be replaced with gamma. So W, sorry, 2 to 3 will be, it will be the same equation, but then instead of T1 and T2, it will be T2 and T3, and instead of N, it will be gamma. So again, we will use the same relation. So we know the final pressure. So T and T2 and T3 will be related as T3 is T2 times P2 by P3, but instead of N, you will have gamma. So you can use these relations to calculate T2 and T3. So if you solve from this, I get T2 around 36, and if you use this relation, T3 as 22.3 Kelvin. So once you have T2 and T3, you can calculate the work done directly. So what would be the work done for the first case? Okay, I need to calculate mass also. So in order to calculate the work done, I would be requiring mass as well. So how do I calculate mass? Use idealized relation. PV equal to MRT. So M is PV by RT. So I'll use equation state 1. Pressure is 2 bar. volume is 5. What should be the value of R? So here we're assuming air. So for air, the value of R should be, again, the units have to be taken consistently. We'll be using units joule per kg Kelvin. So this will be 287. This is coming to around 10,861, 11.61 kilograms. So I have the mass and temperature, so I can directly substitute. I'm directly, like, I'm leaving the calculation to you. T1 and T2, T1 is less than T2, so the work done will be negative. So that is minus 0.7 kilojoule. Similarly, you can calculate for process 2 to 3. Here T2 is greater than T3, so this will be positive work. So that is 858 kilojoule. So once I have 1, 2, and 2, 3, I can calculate the net work done. So this is straightforward work done calculation. Now, how do I calculate the entropy for the first process? The first one is a polytropic compression process. We have already derived the relation in the last week. So this is the relation. So we know M, we know gamma, we know N. Gamma, you can take it as 1.4. N is given as 1.3. We know T1 and T2. So how do I calculate CV? Yeah, from R and gamma, we can directly calculate CV. So CV is given as R by gamma minus 1. So you can substitute that and calculate change in entropy for the process 1 to 2. So you can just tell me the value. You can just check and confirm if you're getting the same value. So is this okay? Like, my entropy is negative. So is this fine over here? So in a compression process, can entropy be negative? So how do you explain this particular thing? So that entropy being negative in the process 1 to 2. Process 1 to 2 is basically an polytropic compression process. Yeah. So how do we explain that entropy is negative? So is it okay or not okay, or why is it okay? So you think this is fine, or is there anything wrong that we have done? It's correct. So how do you explain for the negative entropies? Hmm. Less disorder. So so if your entropy is decreased, which means the disorder is decreased. Okay, you want to put it in terms of disorder. Yeah, since it is a reversible process, when we meant delta S to be negative, so but the delta S total universe should be positive, which means the change in entropy for your surrounding should be higher than this one. To put in other simple words, your delta S is negative, it only means that heat is rejected to the ambient. So in a polytropic compression process, the system actually rejects heat to the ambient. Since it is leaving heat, you have a negative entropy for the system. The surroundings will absorb the heat, so it will have a positive entropy change. Now for the second process is straightforward. It is expanded adiabatically. So for an adiabatic process, the heat exchange is zero. So delta S will be zero. Now, if in this particular question, if the ambient temperature is also given to you, let's say if the ambient temperature, this is around 27 Celsius and it is rejecting heat to the ambient, and the ambient temperature, let's say, is around 25 Celsius or something, then you should be able to calculate the net change in entropy for the universe. How would you do that? Yeah, yeah. How do I calculate the change in entropy for the ambient? T ambient is known. How do I calculate Q ambient? Minus Q12, and we can calculate the Q for a polytropic process. We know W. We can calculate delta U between T1 and T2. We know T1 and T2. We know M, so we can calculate delta U, and from there you can calculate Q, and minus Q12 will be Q ambient. And when you do this one, you get delta S ambient. You can check if delta S12 plus delta S ambient is greater than 0 or not. Should it be greater than 0 or equal to 0? Okay. Maybe I'll leave this as an exercise. You can try this later. Will it be greater than 0 or equal to 0? Like, isn't this a reversible process? So, so we are saying this is a reversible process. Like this compression is a reversible process. If when you solve this, then let's say it is greater than 0, then you can explain why it is greater than 0 even for a reversible process. So where is the reversibility coming up? Maybe I leave that as an exercise. You can do that later. We go to the next problem. So this is again a standard case. So we have already derived equations for certain cases when we have constant specific heats for whichever process it is. In all of these cases, we have a specific heat which is not changing with respect to temperature. But you may have cases where these properties change with temperature. So you can have Cp as a function of Cp and Cv as a function of temperature. Then what would you do? It's just a matter of calculus. So maybe you can take a couple of minutes and solve it. I know the initial and final states. So given these states and given these equations for Cp and Cv, you have to derive the equation for the entropy change. Assuming this relation is still valid, Cp minus Cv equal to R, and R is constant. So how do I get delta S for this case? We always start at the same equation, and then we use the relation. We use the first law, and from this you can calculate du as mc dt and dw as pdv, and then you can substitute and integrate. So give it a try and let me know if you're getting it. That is for the second case. Like first to derive an equation in terms of a and b, then we can substitute that value directly, right? So are you getting the same relation? So are you getting the same answer? Okay. So were you able to get the same answer? Okay. Okay, fine. Sure. No issues. Take your time. The final value. Hmm. Yes. Hmm. So you got unit kilojoule per Kelvin. But I've already given the mass, so you can multiply with mass to get, this is kilojoule per kg Kelvin. So you can multiply with mass to get the total delta S. Four point two six eight kilojoule per Kelvin. Now let us say, if I ask for, suppose for this particular gas, I mean something like this, A plus KT and B plus KT, for this particular gas, if it is going in adiabatic process, what would be the PV relation or TV relation? For the above gas, if it is say adiabatic process, what would be the process equation? So it won't be PV to the power gamma equal to, let's say like previously what we had is in terms of, for example, here we have in terms of T and V. So we usually have TV to the power gamma minus 1 equal to constant, or gamma you can write it as Cp by Cv. So this will be Cp by Cv. we have something like this. So if can I substitute this and say that TV to the power CP and CV are A plus KT and B plus KT. Obviously, this is not true, right? So can you derive this relation for this particular gas? This is actually straightforward, so maybe I don't want to spend much time on it. All you have to do is put S2 minus S1 equal to 0. So if you keep that equal to 0 and then just rearrange these terms, you'll be able to get that. If I keep this equal to 0, I have B ln T2 by T1. So I can just convert this entire expression in terms of ln. So that will be like ln of T2 to the power B times you have K T2. I can put it as e power, maybe I'll put it as exponential of K T2. And similarly, the other term I can put it as, I can again multiply that with A minus B times B2 to the power A minus B. This should be some constant. Okay. So this is clear, right? If I just take these terms and group them together, so it will come something like this. So instead of this, you will get this relation. T2 to the power B and exponential of K2 and V2 to the power A minus B equal to constant. That is straightforward. Okay. We'll move on to the next problem then. So you have an insulated vessel that is divided by a rigid conducting diaphragm. Conducting in the sense the heat transfer is allowable into two chambers A and B, each having capacity of 0.25. So it's exactly half and half. Chamber A contains air at 1.4 pressure and 290 Kelvin temperature. And the corresponding parameters for air in chamber B are, instead of 1.4 you have 4.2 and instead of 290 you have 440. Calculate the final equilibrium temperature, final pressure on each side of the diaphragm, and the entropy change of the system. So even before solving the problem, so will the entropy change be 0 or positive or negative? Without even solving the problem, can you say anything? Can you comment anything on that? Like without solving the problem, can you comment on whether the entropy change will be 0, positive or negative? It should be 0. Why? First of all, it is an insulated system, so there is no heat exchange with the surroundings. So whatever entropy change happening should happen only within the system, and the question also asks about only the system. So the system is equal to your universe since it is insulated one. So the entropy change for your entire universe should either be 0 or greater than equal to 0. So if it is a reversible process, it will be 0. So is this process reversible? Sorry. Okay, it's not reversible. Then what would happen to delta S? It should be strictly greater than 0, right? If it's an irreversible process. Yeah. So your entropy change should be a positive number. So you can verify that by solving this. So how do you find the equilibrium temperature? First, we'll take all the given information. So I'm just denoting one for, okay, let's say A and B, or 1 and 2 for A and B. That is better. V1 is 0.5. What else do I have? Sorry, V1 is 0.25. Yeah, V1 is 0.25. Then do I have P1 is 1.4 and T1 is 290. It is already given in Kelvin. Similarly, V2 is also same. P2 is given as 4.2 and T2 is given as 440. So first thing, how will I calculate the final temperature? So one thing is clear, whatever is the final temperature should be same for both the chambers. Like it has reached an equilibrium. So fine, sorry. So how do you say it is mean of the temperature? Is it equimolar? Both have the same volume, but the pressures and temperatures are different. So number of moles will be different in container A and B, right? Like part A and part B, chamber A and chamber B. Yeah, so the first step would be to calculate the masses. So M1 is P1 V1 by RT1. So you can calculate that. So P1 is 1.4. Point 42. Okay, I'll directly write the value 0.42 kilograms. M2, so you're using R value of 287, right? Okay. 0.83. Okay. So you have M1 and M2 and they're different. So what will be your final temperature? Now you know their difference. What would be the final temperature? You just take the weighted average, right? So what is it? So final temperature will be M1 T1 plus M2 T2 487 Kelvin. How can it be 487? It should be between 290 and 440, right? So I'm getting 389.6. Okay. So now what is the final pressure? So will it be same in both the containers? Sorry. Hmm. Initial pressure is 1.4 bar and the temperature is how much? Less than double, na? Temperature, it's a constant volume process, so it is 1.4 bar and your temperature is less than double. So your pressure should also be less than 2.8. No, we are not removing the diaphragm. So yeah, so the pressure that you told now is for chamber A or B? No, once okay. I think there is some misunderstanding. So the whatever diaphragm is there, the diaphragm is still there. The diaphragm is not removed. It is a conducting and rigid diaphragm. So there is no mass transfer that is happening across the diaphragm. I mean, the diaphragm is still intact. So both the chambers are constant volume processes. Yeah. So basically, P1 by T1 equal to P2 by T2. I mean, P1 by T1 equal to PF by TF for chamber 1 and chamber 2 separately. Then you can calculate the pressures. So for the first one, it will come out to be around 1.88 bar, and similarly for the second one, sorry, getting the same answer. Sorry. Oh, sorry. Okay. Basically, this will be your initial pressure times final temperature by initial temperature, which is coming to around 1.88 bar. No, basically it's a constant volume process. So P1 by T1 is P2 by T2. So P final equals to 1.4 times final temperature by initial temperature. That should give you the final pressure. I mean M1 R. Sorry. So you are getting a different answer when you use this ideal gas relation. How will it be different? Let's just write it down. So you are saying if you put mass one is same, na? Yeah, it should be same anyways. So similarly for the second one, you can get PF2. 4.2 times 389. This should be less than the previous one. 440. 3.718. Maybe I'll just round it off. 3.7. So now how do I calculate entropy change for the first and second process? I mean for the chamber 1 and chamber 2. So it's a constant volume process. So you can directly use the relation mCV or M1 CV ln P2 by P1, or is it P1 by P2? T2 by T1. Okay. It's equal to P2 by P1, whichever way you prefer it. You can directly substitute the values. So M1 is 0.42, CV is 0.7175 times ln T2 by T1 Similarly, you can do for the second one also. Okay, I should have kept differently. Okay, this should be df1 by d1. And this comes out to be minus 0.073. Once you have delta S1 and S2, you can calculate the net change in entropy for the total system. Which is positive, just as like since it's an irreversible process, it should be positive and it is positive. So this is clear. So are there any questions in this or you getting the same answer? Okay, we move on to the next problem. A certain gas has a specific heat at constant volume of so and so. When it is expanded reversibly and adiabatically from a specific volume of say 0.0624 and a temperature of 530 to a specific volume of 1.186 and temperature falls by 165 Kelvin, and then it is expanded into an this is a different process. That's the first process. Second one, when it's expanded into an evacuated space from the same initial condition to the same final specific volume, its temperature falls only by 25 Kelvin. Maybe I'll split it into two parts. So this is the process one and this is process two. Both of these processes have the same initial state, same final specific volume, but temperatures are different. Find the change in entropy in each of the adiabatic processes. Like expansion into vacuum is also an adiabatic process. The other one is like both are adiabatic processes, but the temperatures are different. How do you calculate the entropy changes? First, we'll just write information that is given. Cv is given as 1.25 kilojoule per kg Kelvin. And then I know the initial volume or maybe specific volume. Temperature falls by 165 Kelvin, so that should be, so this is given. So what kind of process is this? The first one is an adiabatic process. So what should be the delta S for this process? Because it is, now for the second case, when it is expanded into space, then what would be the delta S? So what process is that? No, I already told you, right? Temperature falls by 25 Kelvin. So it's not isothermal. Okay, so why are you calling it a polytropic process? So I know V1, V2, I know T1, T2. So how do I calculate delta S? Yeah, it's the same specific volume is the final state, like 0.186 and 0.186. Maybe let me put a different value here. So let us call this S so that there is a differentiation between these numbers. This is an isentropic process, so I'm just using S there in the subscript. V1 is same, T1 is same, T2 is not an isentropic process. Now can you, like we solved a similar problem in the last week as well. So you don't know the process, you know it is an irreversible process, and what do you do? Change in entropy is a it just depends on the initial and final states. It doesn't worry about what process is happening. So all I need to do now is construct a reversible process such that this is a final state. So what would be that reversible process? So can I do something like 1, 2? I know already know 2s, and from 2s to 2, can I do this? 1 to 2s is isentropic. So 2s to 2, what is happening from 2s to 2? No, no, 1 to 2s is the expansion. So I'm basically the process is from 1 to 2. I'm splitting it to an intermediate step. Yeah, yeah. 2s to 2 is a constant volume process. 1 to 2s is your expansion, isentropic expansion. So basically, it will be isentropic expansion followed by constant volume. So now, what would be a change in entropy for the second process? First process delta S is 0. We already know that. For the second process, it's a constant volume process. So entropy changes mCv ln T2 by T2. You can directly substitute the values. So, but instead of, so we are always dealing with specific volume here. So I'm just removing the mass. We are assuming per unit mass of the substance. So Cv ln T2 by Ts. You already know Cv 1.25 times ln T2 is 505 by T2s is 365. That is around 0.405. Okay. So this is a standard thing. Whenever you do not know the process that is happening, but you know the initial and final states. The point here is you know the final state. As long as you know initial and final state, you should be able to calculate delta S. You do not need to know the process that is happening. It's the same thing that we discussed last week as well. So, are there any questions in this? Okay, we'll move to the next problem. This is more of a derivation that you have to do. The heat pump is operating between two identical bodies which are at temperature T1 and cools one of the bodies to a temperature T2. Prove that for this operation, the minimum work required by the heat pump is so and so. So whenever we say that is a minimal work, the heat for a heat pump, minimal work is obtained for a reversible process. So we'll assume that the delta S is 0. So keeping delta S equal to 0, you need to derive the relation for work done. So again, as usual, basically you have a source which is at temperature T1, and then you have a sink that is at temperature T2, heat pump operation, just like what we have done maybe a couple of weeks before. And then you have your heat pump here. What would happen is you supply the work to the heat pump, and you take heat from the sink, and the heat pump will give it to the source. This is the general thing. Say this is Q2 and this is Q1. With this in mind, so how do you derive it? How do you derive the relation for work done in terms of T1 and T2? One more thing they are saying is for minimum work done, the process has to be reversible. So which the process is happening inside the heat pump. So if you consider your heat pump as your system, so the net entropy change for your heat pump should be 0, which means so you have the heat from the sink. So it will come out to be Q2 by T2. That is a heat addition minus Q1 by T1 equal to 0. Can I write this relation here? So, but the problem here is if I write this relation like this, you are assuming that your T2, T1 are what to say, like how do I put it? These are infinite reservoirs. So, is that assumption correct here? Like this relation is valid only if your T1 and T2 are constant. So then we derive the Carnot cycle and all these things. We are based on the assumption that the source and sink are infinite reservoirs of heat. So like by removing adding or removing the heat from them, their temperature does not change. Essentially, they have infinite specific heat. But here I am saying that Cp is a specific heat and it is not infinite, it's some finite value. So if you are taking heat from it, the sink temperature will decrease. If you are adding heat to it, the source temperature will increase. So instead of writing in this form, how do I convert it? I'll just put it as Cp dt1 by t1. This is for the first one, and the negative of the other one is Cp. Okay, it should be reverse minus minus. If you just remove the minus and convert everything into plus, that will be Cp dt2 by t2 equal to 0. And you can do the integration now to find the final temperature. The final so finally, when will the heat pump stop operating? Is when the both the source and sink temperatures are same. That's when it will stop. If you just do the integration between the limits, let's say the initial temperature is T1 to the final temperature, call it say T final. Now we have two of them. Similarly for the second one, you're going from T2 to the final temperature should be same for both of them. So you can do the integration and get the final value of T final. So it is coming. So if you do this, this will be ln Tf by T1 and this will be ln Tf by T2. Okay, I think we have missed something here. So it says that the heat pump is operating between two identical bodies which are at temperatures T1. So both the temperatures are T1 initially. So this limit is from T1 for both of them. And then it says that and cools one of the bodies to a temperature T2. So only one of them will get converted to T2. So this is like this. Is this clear? So one of them is getting cooled from T1 to T final. The other one is changing from T1 to T2. So once it changes to T2, then we are stopping. That is what is given in the problem. Hmm. No, no, there is nothing like that, right? Integration limits can be between initial and final states. There is nothing like smaller and bigger, right? If it is other way, then that basically means that there will be a negative sign that is coming. So what is this equation giving you? Ln Tf by T1 plus ln T2 by Tf equal to 0. So if you do the math, so this will be, sorry, T2 by T1. So Tf will be T1 square by T2. Is right, right? You got the same thing or you got something different? Once you have TF, then you can directly calculate your work done. Work done is basically Q2 plus W should be Q1, so work done will be Q1 minus Q2. So your work done will be Cp times this is for the one, and the second one will also be same, minus Cp times your, it's just matter of substitution. This will be Tf minus T1. Tf is this one minus T1 minus T1. T1 gets cancelled, and then you will get the final answer as W is Cp times T1 square by T2. Oh, I think these are not getting cancelled. This is minus T1 and this is minus T1. So minus 2T1, and then you have minus of minus plus T2. So this is just more of math, nothing else other than that. All that you have to know is the source and sink temperatures are not constant. Then you have to just perform the integration. You cannot write this equation. This is not valid. Okay. I think there are no questions in this, so we can move to the next problem. Okay, here we have three sources. So and they are connected like this. So source one, source two, are both are they adding to heat engine, and then it is rejecting heat to sink. Okay, maybe I should have put it as sink, or let's put it as source. But this is the final sink that they are going to. Q1 is given as so the net work done is given as 200 kilojoule per minute. And okay, I think this is a typo. Q1 is the heat that is being taken from the source, this one, source one. Determine the heat interaction with uh, other two sources of heat, so source two and source three. Evaluate the entropy change to each heat interaction with the engine and total entropy change during the cycle. So first thing is clear. The last one is you already know, since it is a reversible cycle, then total entropy change should be zero, and that is how we are going to derive all the relations. So how do you solve the first question? Yeah, inequality. So what is given to me? I know W is 200. I'm just not writing the units. Q1 is 1500. So if you write Closest inequality for heat engine, what would be the equation? Q1 by T1, Q2 by T2 minus Q3 by T3. equal to 0. Since it is reversible, that will be equal to 0. Out of this, you know Q1, Q2, Q3 are unknown, T1, T2, T3 are known. So basically two unknowns, one equation you will not be able to solve. So what is the other equation? See, all the equations in this course will be either first law or second law. So you have used the second law to get one equation. So the next equation will come from first law. So what would be that equation for first law? You apply just standard, yeah. So work done is Q1 plus Q2 minus Q3. So this is the second equation. So we have these two equations you can solve, and maybe you can tell me what is Q2 and Q3. So you know work done is 200, Q1 is 1500, so you can substitute that. Sorry, 60? No, but the work done is also per minute. Are you getting the same answer? Yeah, so what do the negative signs here mean? Q2 is negative and Q3 is negative. Sorry. Yeah, so basically whatever arrows that I've kept here are just wrong. So this is going in this way. Q1, Q2, Q1 is the same 1500, but Q2 is reversed and Q3 is reversed. So we have this also as sink and Q3 is the reverse thing. So heat comes in from 500 Kelvin, 300 Kelvin and leaves to 400 Kelvin. That is what it is. So now the next question asks you to find the entropy change to each here in each of these heat interactions that you have anyways done just now. So for the first one, it will be Q1 by T1, second one, it will be Q2 by T2, and third one, it will be Q3 by T3. So I'm just not doing that. So entropy change is straightforward. It's basically Q by T. So you can do that and you can see whether it is getting equal to 0 or not. So we use this relation to derive your Q2, Q3. So anyways, it is going to be 0. I'm just not repeating that calculation. That is fine, right? Okay, so we'll move to the next problem. Again, here we have specific heat as a function of temperature, but then it is not linear, it is non-linear, where Z is given some specific value. A system is originally at 250 Kelvin and a thermal reservoir at 125 Kelvin. So the system temperature can change because the specific heat is not infinite, but then the reservoir temperature is 125 Kelvin, and this whenever you say reservoir, the temperature is not going to change. So that is at 125 Kelvin. Determine the maximum amount of work that can be recovered as the system is cooled down to the temperature of the reservoir. So basically, when you connect this 250 Kelvin to 125 Kelvin, this will gradually lose its heat. Eventually, the heat engine will stop working when 250 Kelvin drops to 125 Kelvin. So what is the total work that you obtain from the system? How do you calculate this? So you again use the same thing that we have done just now. So Q1 is the heat from your hot source. So that is integral CVDT, and the limits are between initial temperature is 250 Kelvin and final temperature is 125. So this is Q1. So when will it be maximum? Maximum amount of work is again for a reversible process. So what would you do next is basically put the entropy change equal to 0. So how would I do that? So how do I calculate Q2? So what should I write here? So this is clear. Okay, I think there needs to be by T over. So this is the total entropy should be 0. So Cv by Tpt, this is for the hot one, hot reservoir, or basically the hot, it's not a reservoir for the system one or the source. Now for the sink, how do I write the entropy change for the sink? It should be Q2 by T2. There is no integral because the temperature is constant. Now how do I calculate Q2? So what other equation do I have? So is it clear? You can write this, like from this equation, you can write Q2 as T2 times integral. I'm just taking it to the right hand side, interchanging the limit so the negative sign gets cancelled. Cv is z times t square by t will be zt dt. So you can do the integration and calculate Q2. So what is the value of Q2 you are getting from this? Once you get Q2, the question asks you to find the maximum amount of work. So work is Q1 minus Q2. That's all right now. T2 is 125 Kelvin. These are just a manipulation. Just substitute the values and you get the value. This is 0.045. So no T2 and Z. Once you substitute that, you will get Q2. I'm getting a value of around 131.835 kilojoule. So you can just confirm if you're getting the same thing. Similarly, Q1 you can calculate here. Okay, what about Q1? If you do the integration, so CV is ZT square, so that will be 0.045 times T cube by 3 is 125 cube minus 250 cube by 3. This is Q1, so I can substitute to calculate the value. Okay, the notation is already taken care of, so I'll just write it this way. I think I messed up with the notation somewhere. So the Q1 that we have defined here is from 250 to 125 is the heat rejection from the system. But if you are writing for the heat engine, it will be reverse of this one, right? Okay, that I think I messed it up there. So minus Q1, Q2 is the heat rejected from the heat engine. It should be minus here. Okay, and remove the minus from here. Okay, is this clear, the first part? So when I write the integral, there should be a minus here because this is the heat that is being added to the heat engine or the heat rejected from the system. Integral CVDT is the heat ejected from the system, so negative of that will be the heat added to the heat engine. So you're getting the same answer? So the notation is clear, right? There is no confusion. Okay. Move on to the next problem then. This again is straightforward application of your second law. So you have an insulated air duct, so the net Q should be 0, in which air is flowing steadily. The pressure and temperature measurements are given. Establish the direction of flow of the air duct. So is it flowing from A to B or B to A? So how do you know that? Basically, you'll assume the process is from A to B, calculate delta S and see if it is getting positive or not. If it is negative, then it will be from B to A. So how do you calculate delta S? So which process is happening inside the duct? Okay. So what is delta S? So what is happening? So okay, first of all, so what happens inside the duct? So why is the pressure decreasing and temperature decreasing? So what in any, for example, if you consider adiabatic process, so it is either adiabatic expansion or compression. In one of these, let's say adiabatic compression. So what would happen to pressure and temperature in adiabatic compression process? In adiabatic compression process, your pressure will increase and temperature also increases, right? In adiabatic expansion, it will be just the opposite. Your pressure decreases and your temperature decreases, like you're pumping your car tire or whatever it is. So this process is adiabatic in the sense it is an insulated duct. Maybe I should draw a diagram or something. How should I put it? Okay, so let me put it this way. Okay, so I understood you. So you're basically saying since the duct is insulated, there is no net heat interaction to outside, so delta S is 0. Oh, sorry, delta S surroundings is 0. So, but then internally you're assuming it to be a reversible process. Okay, let's say it is not reversible. So from station A to station B, you are moving. So within this process is not reversible. I gave you the states. Pressure and temperature is already given to you. And this is not a system. So it's just a deviation from whatever we have been discussing up until now. Up until now, it is a system. But now here there is a flow that is happening. So this is not a system approach. It's like your control volume. Sorry. It's like an open system. So you have air moving from point A to point B. And that's why we are not using the volume, but then we are replacing volume with your specific volume. So essentially your density or whatever it is, 1 by rho. Specific volume is 1 by rho. So you use this particular relation to relate between this. So if I know pressure and temperature, I also know the specific volume, right? So I can use ideal gas law to calculate the specific volume. So I know initial state and final state. So just as it is, I do not have to know the process that is happening. As long as I know the initial and final states, I can calculate the entropy change without knowing what is the process that is happening inside. So with that logic, can you calculate delta S between A and B? So which relation will you start with? I cannot start with directly with the first law, Q equal to U plus W, since this thing is a flow process. So which relation I'll use instead of U plus W? Delta Q is, let's say I put it in this way. You will anyway start with this and then, but then U and W I cannot calculate directly. What will I do next? Can I write it this way? You see where I am going from this? Maybe I should have used little little W. Is it clear up until this? And dq, how can I write dq as? Can I write dq as dts? I think now you will be able to calculate. So I have the relation between ds and this one, and dh I can write it as cp dt minus v by t dp. So from this, I think you will be able to solve. Now you have the relation between entropy ds and dt by t. You know the final temperature, initial temperature. All I have to do is replace this v by t, and the question it is given as v by t is r by p. So you can substitute that. Cp is also given. So now you can do the integration and tell me what is the value of delta S you are getting. Just take care of the units. Are you getting the same thing? Yeah, sure. Yeah, so see, this should be positive, but we got negative, which means the flow is from, like, we require delta S to be positive, which is not happening here. So the flow is from B to A. So everything is same as we have done up until now. The only difference is that here there is a flow process. Instead of per system, we use control volume. Then we will actually look up more control volume problems in the next week. I don't know if it is there as part of the syllabus. I'm not sure. Like, is it already covered? Have you gone through week 12? I haven't gone through them yet. Okay. Okay, then maybe if it is Rankine cycle, then it is part of it. So we'll discuss next week then. Like more into flow process. Sorry. Yeah, delta is less than 0. So we assume it is from A to B. Since it is less than 0, the flow is from B to A. We require delta S to be greater than 0. Yeah. Okay. Now is it clear? Yeah. So the next one is also a very straightforward problem. You have the water at two different temperatures getting mixed in an isolated system. Again, the same thing. Since it is an isolated system, delta S should be greater than or equal to 0. But the mixing is an irreversible process. So how do you calculate the entropy change? This is again is not an infinite reservoir. It has finite specific heat. So you have to do the integration and then calculate the final change in entropy. So what is the final temperature? Final temperature calculation is straightforward. So final temperature, you just take 3 times 80 plus 4 times 15 by 7. What is 42 point something? You can get the final temperature directly. That's not a big deal. So how do you calculate the entropy change? That's the question. So I have T1 and T2, I have TF. So what is a change in entropy? So which equation will you use out of these relations? Can I use any of these? So when we have this mixing that is happening for water, so it's a constant pressure process. Like it is happening at atmospheric pressure. When this mixing is happening, this is happening at some fixed pressure. So all you have to use is the constant pressure relation. So delta S is straightforward. So you have the mass of them. You know the Cp of water. It's around 4.186187 something, whichever you want to use, into ln T2 by T1. So for the first one, the temperature, final temperature is 315.85 divided by 353. And for the second one, the mass is 4, final temperature by initial temperature. This is a very straightforward problem, so I'm not spending more time on that. Now, this is an extension of the same problem that we have here, but then you need to determine the final temperature in terms of your initial temperatures. So like here I got a final temperature as this one. So will this be the same always? So it's the same relation that you have before, but then T1 and T2 instead of numerical values, I've just kept some variable names T1 and T2. So the final temperature, since the mass is same, will be T1 plus T2 by 2. If you substitute that in the entropy equation, you will get it as delta X is MCP will be constant times ln will be Tf by T1 and Tf by T2. So that will be Tf square by T1 T2. Is this part clear? Then you can directly substitute this T1 plus T2 by 2 here, and then you will get the final equation. This is a very straightforward one. So it turns out that the equation comes out as 2mCp non, we'll let it as 0.5 T1 plus T2 divided by something like this. So it's basically arithmetic mean by your geometric mean. And this quantity over here is like T1 and T2 are always positive or greater than 0 from third law. So this is always positive. So delta S of the universe will always be positive. So whenever this mixing is happening, it will always be an irreversible process. That is the only thing I wanted to show from this relation. This is always irreversible as long as your if T1 and T2 are different. So any mixing that is happening at a finite temperature difference is an irreversible process, however small the temperature difference is. That is the only conclusion that we have from this. Yeah, these are the problems I have for this. So you have any questions? Sorry, you have something? Okay. Okay, I'll stop sharing. Yeah, I can see your screen. Mhm. Heat capacity of water is 4.1 support or water. Okay. You need to find the final temperature. So how do us like what did you use here? Maybe you can share your working also. No, maybe you can just tell me what you have done. Then you can share your working in the chat box. So basically m dot into Tf minus 10 equals to m dot h. So basically m dot h, m dot c are same. So 90 minus Tf equal to Tf minus 10. That's what you have done. Hmm. Okay. But then that, no, that would be not the final Tf, right? Because heat loss will not be same for both of them because you have a heat engine here. So QH is basically your m dot h into Th minus Tf, right? And Q dot C is your m dot C Tf minus 10. Now you have a heat engine between them. So what do you do when you have a heat engine? Is you apply that second law, like from process inequality, what you have then? QH by Yeah, now you have to do the second part. You have to integrate the same thing that we have done till now. So your integral QH by TH minus QC by TC should be equal to 0. But basically you apply your process inequality where QH is MCP DTH and QC is MCP DTC. Okay, first thing, did you understand your mistake? Yeah, QH should not be equal to QC. So that is the first part. Now the second part is if QH is not equal to QC, you need to find a relation between them that comes from the process inequality. So just see the that just we have derived. So MCP dt. So it will be MCP ln TF by TH. Same whatever we have derived just now. Try that once. Hmm. Sorry, he told it is following a Carnot cycle, right? It was mentioned that it's a Carnot engine, right? No, that is, see, basically if QH equal to QC, then obviously work done will be 0. QH minus QC is 0. Hmm. Yes, yes. Hmm. There, work output is 20.8 is first option. And what is your final temperature? Okay, so you're saying that is not the correct answer. But no, but the process is the same. Like just now, what for you assume a Carnot engine. So basically, you'll integrate the entropy change and keep it equal to 0. From there, whatever temperature you get, that is the final temperature. And once you have the final temperature, you calculate QH, QC, and W. Mhm. Okay, so you're saying there is some calculation mistake or something. So, but the process is correct. Whatever you told, you integral MCP, that is correct. How did you get 50 degrees Celsius? Is basically m dot QH equal to QC. That's what you did. Oh, no, no, that is not correct. No, you cannot equate QH equal to QC. The one that you did previously is correct. Like entropy thing is the correct way. So did you convert the units appropriately? Yeah, then it's correct. The entropy one is the correct one. 323. Yes. So that is okay. Yeah. Then that is it. Okay. Thank you. Then we'll meet next week. Thank you for joining.